So the presentation, the title of this talk will be Understanding Fracture Framework using Diffraction Imaging Technology. So we'll be discussing today about the fractures and then natural fracture network and how to image this. So let's start with why. Why do we do that? Why it's important to do the fracture analysis and the fault analysis in our data sets and in our areas, right? Well, first of all, the faults can be hydrocarbon traps. So they can actually be they can create reservoirs, of course. Then you can start discussing about the faults. Are they open? Are they closed? What the materials they are filled within? So you can then talk about that. So you can actually see if they're open or closed. And then you can start to if you know more about this fault the geometry, and you can start talking about the production flow rates, how the eventually hydrocarbons can flow actually through the open or you know close the faults. So you can impact by knowing that information. So you might actually impact your production flow rates. Is it more permeable or less? So these all information are really important to bring up in the interpretation and understanding the reservoir itself and their compartments and everything, right? Well, the structure forms like faults, unconformities, karsts. They are actually source of the diffraction energy. As soon as you have any kind of edges of those forms, so they are actually the source of the diffraction energy. And diffraction energy creates that one. And then in the inverse, now you can actually use this diffraction energy to actually image the geological feature we are looking at to image. Well, there are some challenges for that. That typically you have those larger faults that you can see them on the reflection data, because typically you have a reflection data and you have a diffraction data, right? So those even larger faults, they can be actually seen on the reflection data. But the small faults with a very small displacement, well, after you do the stacking, then you have actually problem imaging this, because they're going to be gone from after the stacking process. And then I'm going in the remaining of the talk, I will be talking about why you are actually seeing that. Okay, so how we actually first try to image we are imaging the diffraction energy, how to capture it. So to do this, so we are actually using here something called Earth Study 360 migration, which will actually illuminate it. It goes from the bottom up approach, and it actually illuminates the surface, so that will actually enable us to whole seismically recorded field to decompose in the 5D domain. And then when we are scanning, we're actually scanning all these directional dips and azimuth, of course, along with all these opening angles. And that you can maybe image yourself as a flashlight that you are actually going from the subsurface and you are illuminating the surface. So you can imagine that, and then the width of the flash, and then position of those flash. These are the angles we are actually discussing. Okay, so let's see in a little bit more of details how that works, how we are decomposing this. You know, what we would like to call it local angle domain, or you might see this somewhere. It says LED. Okay, so you have a subsurface point. Let me just start my laser. You have a subsurface point here. And then from that subsurface point, we can shoot the rays towards the shot and towards the receiver. And then those two rays can be actually positioned based on the structure itself. So let's see what kind of a decomposition we can do this, what kind of angles we can actually see from there. So you have a dipping structure here. And then this deep structure has directional dip. And it can be actually directional azimuth of those structures. These are all structure that depends on the structure itself, right? So we can, as we know, it's a directional azimuth and directional dip. That's how we call it here. So these two angles, so you can decompose those. The other two angles, you have to think about this in the 3D sense, by the way. The other two angles, so you can actually have the angle that are actually those half opening angle. So this is the angle halfway from the from this incoming and the reflected way. So this is the angle, and then of course those two angles, they can actually be in a particular those two rays, they can actually be in the particular azimuth plane. So you can have now directional azimuth, directional dip, which is a structural component of the decomposition, and then you have here opening angle and opening angle, and then opening azimuth. So those four angles, then we can actually every trace, everything that was recorded, it can be decomposed in those four. Plus the fifth dimension is actually the depth of the subsurface point as well. So once you actually do this decomposition, you're actually in that LED table, let's say. So you can actually see that that we can actually decompose this in a particular matrix like that, LED matrix, right? So then which actually consists in the opening angle, and then which has a rotating 360 degrees of the azimuth, and as well as you can have this deep angle, and then rotating azimuth of the dip of the structure itself. So if you are creating some table like that, so you might actually start to map in each of these cells. You can actually map your information that you are decomposing, right? So you can do this for every bin location in the survey. And out of that, we are actually creating. So out of that, you can actually create, you can represent these directional gathers that the radius of this cylinder is actually the dip, where the dip of 0 is in the middle, and then on the edge of the cylinder is actually the maximum dip, and then the slice of that can be actually the azimuth that you can see. And what you can actually see that there is one particular corridor of the high energy, which is actually what we call a specular energy, and that actually represents the true structure. So by following this this energy here, this is exactly where your true structure is. Okay. So you can see that if you project this, so you can see on the half sphere, this is the dip of the structure as you go up and down and you slice it. And then if you slice in azimuth, so you can actually see the azimuth changes of your structure. Okay. So when you are coming out with these directional gathers, just they're not looking as a regular reflection gathers. So they instead of offset that we have or angle, so this way we have a dip as a primary source, and then the secondary source we have a rotating azimuth of 360 degrees. And then let me just show you how this appears. So the reflection normal energy that you have from source to reflecting back to the receivers, it will be mapped in this domain. It will be mapped actually as a V shape here, right? Where the deepest event will actually be equivalent to the deep of the structure, and then you can actually see that the energy is actually weakening up as you go from the deepest point. In the talk of the let's say if you have a point diffraction, so where energy is actually spread out equally in all azimuths and all dips, so you can obviously see this as a line that connects, because the energy goes everywhere with the same intensity. It goes with the same intensity everywhere, right? So no weakening, no fading out of the energy. And of course, if you have some kind of edge diffractions from the folds, let's say, or the double folds or corner waves, so you might actually see that this is the same energy, but this time it will be actually polarized only in that fold plane dips, but it will actually repeat for every azimuth. Okay, so this is kind of what we are looking at. So in a more practical, okay, sorry, just the workflow to cover first. So we are coming up with a time gathers and velocity models that we developed, as I discussed in a previous talk. We are taking the final velocity model in depth and then the time gathers, using those structure attributes, DAC attributes to constrain the solution, and then decomposition in this case, right? So we are decomposing everything in the LED domain, and then we are coming out with the directional gathers. And then the trick is from those gathers, and that's the key point, how to separate reflection energy and diffraction energy. Remember what we said at the very beginning? We actually have to define, because the diffraction energy is extremely weak, and then after the stacking process, the reflection overpowers diffraction energy, and diffraction energy is gone. So you need to separate them and then create separate stacks for the diffraction energy, and then later on you can stack them individually, right? So then, or you can weight it the diffraction energy to boost, and then you can stack them. And of course, you can later on use some visualization techniques to even enhance the signal. All right. So the gathers, as I said, they don't look so as maybe you expected on the offset, with increasing offset or increasing angle, reflection angle. This time, this is the dip that you're seeing, and then you can actually see if you can just extracted the specular or reflection energy. So you can extract it, and then this is represented that cylinder. And if you're going from the top, so you can see how it's focused, the energy. And if you apply some kind of a diffraction filter, so you can actually eliminate all these high energy. That's where the reflection energy sits, and it's around the dip of 0. This goes from 0 angle to 40 degrees dip. And then in this case, the structure is pretty much flat, so then everything is concentrated around dip 0. So you are actually able to use some diffraction filter and eliminate this refraction energy, and using everything that sits around it. Okay, so let me just, in the 2D case, just to show one example. So this is the stack. There you have a map, let's say three. I marked 3 events, one horizontal, one with a negative dips, and with the positive dips. And in the gather, in the 2D case, so in the middle you have a 0 dips and negative on the left side and the right side. And then what you can see, the event A, so you can see that it's actually pretty much flat. So you can see that, and it's centered around 0. Then the negative dips, this corresponds to the energy on the deeper. And then as you remember, this is where the lowest, the deepest point. That's where the true dip is, right? And then you see on the right side, this is the energy, the event C, right? It's right. So if you can actually corridor, do you remember that from that movie? So you can actually you can use your specular energy, and you can actually just increase the signal to noise ratio, but by eliminating all this distraction around it, right? Around that might be actually from the random noise and everything. As a comparison to the, let's say, Kirchhoff migration, you're not relying on those swings, migration swings to be canceled out, and then you have a constructive interference, what they call it. So you actually can actually use this energy to guide where the true dip on the struct, and then increase the signal to noise ratio around it. Okay, typically what we are looking at the horizon slices. In a 3D sense, so even when you are doing this 3D, you can actually see some hints of the faults and the fractures. But what you see heavily, what is dominated, it's dominated with this reflection energy that sits, and then it's masking that weak diffraction part, right? After application of the diffraction filter, so you should be able actually to remove this reflection energy, and you can now start to reveal the diffraction energy that actually is underlying with a much lower amplitude. So by removing this reflection energy, which is really strong, then that overpowers the stacking output. So then you are actually able to reveal and then see much more detailed image of the fractures that we are trying to image. Okay, so then going further, so you will be able actually even to do some in the visualization part. So you can actually do some spectral decomposition, and then if you have some normal stack, and then I have a normal stack, meaning the full stack with the reflection and with the reflection and with the diffraction energy stack together. So you can see that you still see some of the hints of the fractures, but then by doing this, applying this diffraction filter, so you can actually see that how much sharper and then cleaner image you start to get even in a particular domain. Obviously, you can actually use these other techniques for the visualization part. So this is in a short. So what in general what the techniques will be. And I'm going to show you a couple of case studies, okay, that we did. So we did one in the Neoquim Basin, for instance, there in the Vaca Muerta shale. So first step is making sure that the time processing is done correctly, and then all this depth image is done correctly, and that we didn't attenuate. We have to be very careful when we are doing the time processing, that this diffraction energy is still maintained and not be treated maybe as a random noise and then removed. If you remove this if you remove this in a time processing, so it's going to be almost impossible to reveal. So first of all, we actually this is legacy processing that was done in that domain, and then this is our product that we still using this careful time processing. We were actually able to maintain the structure itself, right? So then those faults are still visible in our updated revised processing. So in this data set particular, there was a big trust, and then as per a geologist expectation, so you have a truss and you have extension on the side, and then what you are seeing in red here, this is where the diffraction intensity is. So so diffraction energy is mapped, and then you can actually see that all the energy is actually only on the one side of that truss, which is exactly lining up with the model that was expected to see all this stuff. So just on the one side of the fault, of the truss fault. Okay. So in order to make sure that that we are correlating, so we would like to very good. So we created most positive, most negative attributes, which is actually post-stack, and it's just a few of them that you see, and then as you can see, you can start to see in the more details in the fracture data set that we have. And then as a client had one so yeah, sorry. We actually run as well thin likelihoods of the faults, and then here mapped in the blue color, and then DI still in that red color. So you can see that this likelihood is a little more chaotic, and then you can see that really good orientation, and then good image of the diffractions as well. So you're actually able to see subseismic faulting and then associated fracture much better. And then as a control well, we had someone that was shared with us. So on the side here, that there was a well here, and it was the path that was drilled. So no fractures was detected, as well as on other or on the geosteering data that was measured in the well itself. Okay, there are a few other stuff from South America as well I have. So this is the area that the client was looking for how to find those compartments, because it's a broken reservoir, and they would like to identify every compartment that's possible, what's talking to what, right, in these compartments. So by doing just a PSDM, we can just see the hint, and then just those big ones that the faults that you have. But using diffraction energy, we were actually able to reveal and then start to see some compartments. And these two images are out of the same volume, but just a little bit more of the energy, how we measure the energy, so we can see some details on the reservoir that you probably won't be able to interpret from the regular PSDM. The other one, other example that we had, so this is obviously this is striking it was good as well on the PSDM, but obviously on the diffraction energy stack, it's really brought the higher resolution for it. So I have the other example here that if you're going from the let's say from this horizon, and then if there is a comparison between the PSDM and the diffraction energy, and then so how to actually get the fractures imaged, so you can see more details, much more than you can see on this stuff. Right? So there is another level, so few horizons that you have. You can see that there's really, you can start to see the faulting that it's happening, what's happening there. And then using those spectral decompositions, you can combine a couple of those that are actually really imaging well it is really imaging well the structure. So if you're starting, let's say from the top to the bottom horizons, right? So you can see that you can actually really see this the fracture that are happening over there. This is when we are using this RGB technique, red, green, and blue. So we are combining three volumes into to create one image with the mixing of these three colors. So, for instance, if you go with so with the one volume, if you slice it, the horizons from the bottom, let's say, go up, so you can see how much of the fracturing systems we were actually in the river channels as well. We were actually able to reveal. So if you go more to the shallower, of course, you start to see the more of the footprint, that acquisition footprint that was there. So since that the fracturing system was actually in the same direction as as faults that we are the client was looking after. So we decided not to remove those fracture acquisition footprints. But if you go deeper, so you can see that everything. So it's a really nicely image. So you can see all these, even you were able to see the river channels, and then delta and all this stuff that the interpreters are looking for. And then of course the structure as well. So you see all these paleo channels and the fracture story. So by using these techniques. Okay. So if you, this is the diffraction part, but what if you are actually just concentrating just on the specular part, right? So we are actually eliminating the diffraction energy, and so this part of the energy can be actually used and help interpreters in interpreting something that is continuous. It actually brings much more the signal to noise ratio, as we discussed, because now you're not stacking random noise, and so you're concentrating on the signal only when you're stacking. So because you know from the diffraction energy where the signal is based on this high amplitude, which it's a part of the specular enhancement. So how we call it. So this is one example as well from the Rockies here, so that you can actually see that is a regular PSDM, and then after the specular, so we were actually able to bring some some of the continuity and the imaging up. So these techniques as well, specular. So if you have a poor illumination, let's say under the truss belt, so you have a problem illuminating that part. So so with the smaller hits, by increasing the signal to noise ratio in this technique using the specular stat, you are actually able to image something like that. So you can see that these images that are coming from the specular stat, using specular enhancement, it's actually creating much cleaner images, and then as well as in the poorer illumination zones, you might actually have as well you might have the better image, right? So there is another example here. This is conventional PSDM stat. This is where the client was focused on, right? This is for marine environment. And then you can see that after the specular, you see that everything is there, and you have a much cleaner image that you have. And then now we can start seeing even something in this poorer, let's say within this poorer zone. So you might actually see what's happening. So more than what you. It's really hard to guess what's happening here, but once you have, so you have a good hint what can happen there. Of course, this, as I said, so that you can actually, by increasing the signal to noise ratio, your continuity will increase, and then your phase stability will be there too, of course, right? And then you can actually, as a result of all of this, you can actually have increased resolution that you have. And then by doing this, so you can actually, if you're, let's say, in a shale play or something like that, where you're actually driving your horizontal wells, so obviously it would be easier to drive the well from using the specular PSDM than actually the standard PSDM, right? So you're more accurate because now you have a high resolution, and obviously you would like to, when you are driving the horizontal well, you would like to make sure that you don't go above the layers above and the layer below, because that's going to, that part, as you get into this part, by mistake, not knowing, not having the high resolution data that the specular image provide, you might actually drive the well into the above or below. So, and that part, until it comes back to the reservoir, it's lost for the production. So with having this specular image PSDM, for instance, you might actually have direct, if you know how to drive, how to steer your well. That means that you will be, well will be more productive in the future. So it will turn into the more money, I guess. Again, production means money. Okay, so that's I guess all what I wanted to show you for this. So now I'm opening the floor for the questions.